And so it's about the possibility to think whether there could be some cosmological implications of Majorana mass generation in the early universe, and whether we could even have some hints. Indeed, at the end, I will show that maybe, if we are lucky, actually, we might already have some hints, even though, okay, it will take some time. And okay, that's maybe an optimistic statement, but there are some interesting developments cosmologically. So I will probably enter in, yeah, in this way, you should see even bigger. So first of all, let me say that, as Antonio was saying, I'm interested clearly in new physics. So as I guess also many of you. And clearly there are different strategies. At the moment, the situation is that there are no clear indications from collider physics. There are anomalies. You pick up the one you like. I don't know. Here now, I'm back from Orion actually. So there are, indeed, it's true. There are, if you look at the experimental summary told, essentially there are no big anomalies. The flavor anomalies are kind of the RK star went away 2 years ago. G-2 also it's not clear. There is this 95 GV also here in Southampton. People are working on that. Maybe you too, I don't know. But it's one of the anomaly that is around. But anyway, and also there are theoretical motivations, but it's also these are kind of subjective. So, but even barring these considerations, what we cannot explain with the known physics are the cosmological puzzles. And here I, in particular, circle the dark matter and matter-antimatter asymmetry of the universe. And together I will refer to them as the problem of the origin of matter in the universe. And also, we need to explain neutrino masses and mixing, that they are the only established evidence of new physics in laboratory, let's say, with human-made experiments. Antonio told me that probably I should have given some cosmological introduction, so to understand better this problem of origin of matter in the universe. So very briefly, I don't know if for you it's maybe it's boring, but please interrupt me whenever you want with questions. So just to remind you, the kind of cosmology I will be interested in, and I will always refer to a universe that is very simple because it's just homogeneous and isotropic. So I will always assume a Friedmann-Robertson-Walker metric. There are no real motivations to go beyond, even though I don't know if you have heard, but there are kind of hints that we live today in a special region of the universe that where anisotropies and inhomogeneity might be dominant, and people are, let's say, theoretical astrophysicists are attempting to go beyond to describe, for example, what happens if you go beyond the Friedmann-Robertson-Walker matrix. I'm just back from a conference that was in London on these aspects. It looks like we are, I don't know if you have heard about this dipole anisotropy tension, but it looks like we are in a special region of the universe that is where there is a bulk flow on a scale that is as big as 300-400 megaparsec. And so some people think that we might have to go beyond the Friedmann-Robertson-Walker metric. But since I will be interested in the early universe physics, actually all these anisotropy hints do not affect my discussion. And so the discussion is very simply based on Friedmann cosmology. And here I just remind you the fundamental equations. One, from Einstein equation, you derive Friedmann equation for the expansion of the universe, for the evolution of the scale factor. And then you have a fluid equation that specifies essentially how the different, once you give the equation of state of the different fluids and the nature of fluids in the universe, they will give you essentially a dependence of the energy density on the scale factor. And of course, some parameters, it's fundamental parameter that we probably all know in cosmology that you can introduce are the Hubble constant, the total energy density parameter, that in the case of a flat universe, however, can be just set to 1. And then the deceleration parameter that here you don't see it, but it can be introduced and parameterize the acceleration of the universe. And this introduction allows me to tell you what is the status, for example, about the Hubble constant. I guess probably you have heard about the so-called Hubble tension. So there are different measurements. Well, there have always been historically an Hubble tension to different some level. At the beginning, Hubble was actually greatly overestimating the value of Hubble constant because of a completely incorrect cosmic distance ladder. But when C fields were better calibrated, then somehow at the beginning of 2000, there was an agreement around 70 kilometers per second per megaparsec. But after these measurements, there were more and more precise measurements, and both from supernovae, the historical one, that reduced the errors, and also now, as we will see, I will talk in a moment, from CMB anisotropies. One is a kind of early universe measurement. Actually, it's an indirect measurement of H0. You measurement quantity at the present from past observations, and this can be done within the lambda CDM model that I will talk in a moment. But directly, some observation seems to give a much higher value. Whether this is a 5 sigma tension is the result of maybe underestimated errors or not, it's under debate. Probably new measurements from the James Webb Telescope. Many groups think that actually in this measurement, there are some systematics that have been neglected, but I don't want to enter this. But I will mention this Hubble tension in the end of my talk. So it's just for you to know. And by the way, we will also talk a lot of gravitational waves that were discovered in LIGO from the black hole merging first. And there is also an event of gravitational waves from a binary neutron star in spiral merger that allowed to measure the Hubble constant in a completely different way. People talk about standard siren because essentially you see an optical counterpart of this event, and also you see gravitational waves, and that allows you to calculate both the distance of the object and also the redshift. And so from the definition of the Hubble constant, you immediately can derive a value, but with huge errors. But people thought in 2017 that since we solved so quickly such an event, we would have immediately have many events of this type, and that this error would have been reduced very quickly. But actually, after this event, nothing else, none of these events has been observed again. So at the moment, from this kind of measurement, this is the value of Hubble constant, and you need 50 more detection of standard sirens to essentially say whether this one is right or this one. Anyway, CMB anisotropies clearly provide nowadays the most accurate and precise way to measure cosmological parameters, including the Hubble constant. And the Planck satellite in 2013 provided the most accurate maps of CMB anisotropies. And let's say these anisotropies can be understood with a kind of simple physics during recombination time, where photons were scattering on electrons through Thomson scattering, and this fluid of photons, electrons, and protons were also clearly undergoing the expansion of the universe. And if you have fluctuations, you have to consider mainly two effects. One is the gravity that will tend to make an overdensity to collapse, and the other one is the pressure of the fluid that will oppose a resistance to this collapse. And in the end, you can show that actually this gas will undergo some oscillations until photons are coupled to electrons. And these oscillations can essentially explain the power spectrum of these anisotropies and also allow you to understand the composition of the universe during this time. It's very similar to the way how you understand, for example, chemists understand how the chemical composition of violins. There was a mystery about how violins were in North Italy, actually, in the 18th century, why they had such a beautiful sound. They studied the sound of the violins to understand what was the trick. And they obtained power spectrum to understand the chemical compositions. And it's very similar. You do a Fourier analysis, and you can extract the parameters in your model. And what happens is that actually the data are very well fit by a very simple model, that is the lambda CDM model, where you have a very minimal number of parameters, 6, if you assume that the universe is flat. And this just with 6 parameters, you reproduce very well this huge abundance of observations. So that's quite impressive. Not only in CMB anisotropies, but many other observations that I don't have time to discuss, but these are the most important. And this shows how the acoustic peaks that you observe when you do this Fourier analysis depend on the parameters of the model. Mainly matter and baryons are those that interest us, but also curvature and dark energy. And so they tell us that the universe is very close to be flat. We don't observe any curvature. You can also, as you can see, it's not very sensitive to dark energy, but when you combine with supernova, we also measure dark energy very well. And we confirm the picture that the universe is accelerated at the present time, that was first discovered in supernova. And then we measure very well baryons abundance and the matter abundance. And what we see is that you can't explain the whole matter just with baryons, but there must be a new fluid that is non-standard that we call cold dark matter that cannot be explained in the standard model. And so that's a big motivation to go beyond the standard model of particle physics. By the way, the same acoustic oscillations are now observed also in the power spectrum of matter. These are so-called baryoacoustic oscillations. And actually, when you combine the two observations, you are really able to also to measure very accurately the dark energy. There was recently the measurement by the DESI collaboration on baryon acoustic oscillation that it's not something I can talk, but it's very important because it plays a very new stringent upper bound on the neutrino masses, by the way. Maybe too stringent, actually. It looks like there is a tension with neutrino oscillation experiment. Please interrupt me whenever you have a doubt or a question. So these are the 6 fundamental parameters in the lambda CDM model, and you can see how well they are measured within the lambda CDM. And these are all secondary parameters that you can extract within the cosmological model. Like H naught is a secondary parameter, and this is the measurement I was showing you before of the Hubble constant. Or, for example, the dark energy is 31% of the total energy of the universe. And the matter is about 31% nowadays, while 5% of which is made of baryons, essentially. The age of the universe also is measured very well in this model. There should be here somewhere the age of the universe. That is, yes, here is about 14 billions of years. So, but focusing on the baryon asymmetry, on the baryon abundance, what we know is that also we do not observe primordial antimatter in the universe. And so therefore we know that nowadays the baryon abundance is also a measurement of the baryon asymmetry of the universe. So the universe, observable universe, essentially is made only of matter and not of antimatter. Or at least we don't see any hint of the presence of primordial antimatter. Well, there are claims that AMS experiment has seen some anti-helium, but that might be an experimental problem. Also, from acoustic peaks, we get a very precise, accurate measurement of cold dark matter, and this is about 5 times the baryon asymmetry, the baryon abundance. And we know also that there is some dark matter at the present time from dynamics of clusters of galaxies and from the galaxy rotation curves. But we know that this dark matter is non-baryonic exactly because it must be produced, it must be primordial, so it must be there already in order to understand the acoustic peaks and also the structure formation. Cold dark matter plays a fundamental role in understanding the formation of galaxies. That's why cosmology provides, gives you this very strong evidence of new physics. What is a natural solution from the origin of matter? Based, when I say natural, because it was kind of based on naturalness, and that's somehow it was a solution that was converging, agreeing with naturalness, with the expectation from naturalness, and for a long time it was considered the standard solution. The dark matter should be a WIMP that is able to weakly interacting with the standard model plasma so that it first reaches thermal equilibrium. And then when the essentially the rate of annihilations decreases because of the expansion of the universe and because of the density of particles that is decreasing very quickly, this density cannot, when the mass is around the temperature, when the temperature drops at the level of the mass of the WIMP, the annihilations cannot anymore so make in a way that the abundance of dark matter tracks the equilibrium abundance, and so there is the so-called freeze out. In order to reproduce the value of the dark matter abundance, we observe you need a value of the annihilation cross-section times the relative velocity, a thermal average, that has a very precise value. Well, these three depends on the mass in the end. So there is a modulation with the mass I will show you in a moment. And when you plug here a weak interaction description of this quantity, you find that the mass of the WIMP should be exactly where you would expect from naturalness, around the electroweak scale. That was the WIMP miracle. At the same time, also, people realize that you can understand matter-antimatter asymmetry of the universe also at the electroweak scale with electroweak baryogenesis, but you need to go beyond the standard model, since in the standard model you cannot have a first-order phase transition that is required in electroweak baryogenesis. So there was a moment where actually these two things seems to be so well in agreement with the naturalness expectation that it looked really like a very attractive package for the origin of matter. What went wrong in this is that, well, first of all, we haven't discovered new physics at the electroweak scale, and I would say that's the main point. And therefore, people started to doubt about this combination. And also, from indirect searches, this is the thermal cross-section that you would expect in order to reproduce the dark matter. From indirect searches, the most you place a lower bound, an upper bound on this quantity, on the annihilation cross-section times the relative velocity, that seems to clash with the WIMP miracle. That doesn't exclude WIMPs, but it's not a miracle anymore. You have to introduce some other parameters. Typically, I don't know, you have heard, I'm sure, about co-annihilations, for example. But this model doesn't seem to be anymore so compelling as in the past. And so that's why there have been many other models that have been studied for the origin of matter in the universe. And probably the most attractive one are based, since in the meanwhile we also discover neutrino masses and mixing, they are based on an extension of the standard model that can also explain neutrino masses and mixing. And as Antonio was saying, I've been studying this kind of extension for a long time. Why? Because you can introduce a right-handed neutrinos in the standard model, in addition to the standard model content. And therefore, you can introduce a Dirac master and also a right Majorana master. And with this simple extension, you can, for example, in the CISO limit, understand the lightness of neutrinos with the CISO formula. But also, you can understand this kind of predict existence of new very heavy right-handed neutrino in this CISO limit. And their decays can be CP asymmetric, and they can produce a matter-antimatter asymmetry via leptogenesis. So you have also so you can explain these two things in a very simple way. And also people have attempted to explain the dark matter from active sterile neutrino mixing. Essentially, within the CISO limit itself, where the Majorana mass is much larger than the Dirac master, you can still have a mixing between the active and sterile neutrino that can be large enough if the sterile neutrino is not too large, too heavy, order of kV. And so this leads to a solution for dark matter or within this mechanism that also was considered very attractive, even though I have to tell you that the dark matter solution now is very constrained from X-ray observations. By the way, a few days ago, actually, we had just had the journal club, and we have noticed that there is a new paper, I think today, of X-ray observation from this X-ray telescope. I think it's called the New Star, I think, something like that, that plays very strong constraints of this solution. Today, I have a personal solution for dark matter that is alternative to this, but today what I want to talk to you about is about another aspect, and the aspect is the following one. So in this extension of the standard model, the Dirac master is clearly generated at the electroweak symmetry breaking, spontaneous symmetry breaking, but the Majorana master is kind of put by hands. So there is not in this bottom-up approach, there is no description of how the Majorana master is generated. Now you can do many things to describe the generation of the Majorana mass. Probably one of the most attractive way you consider a grand unified theory like SU10, and in that case, all masses are generated by a kind of X mechanism, even though the X has to be sector is extended in that case. But probably a simpler approach that is still within this philosophy, a bottom-up approach, is a Majoron model that is very simple actually. So simply you introduce in addition to the right-handed neutrinos, also a complex scalar field. And this term, if at very high temperature, and that has a kind of a three-level potential as well. And this Lagrangian will respect a U1, a global lepton symmetry. When you consider the early universe, you will have finite temperature effect that you have to consider. And if the temperature is large enough, this symmetry is restored. And so this lepton number is non-violated. So you have lepton number conservation in the universe, and the vacuum expectation value of this complex scalar field is 0, essentially. However, when the temperature drops down, there will be essentially a critical temperature where there is there is first a formation of a temperature where you form a second minimum in the potential. And when the temperature drops to below a critical temperature, this minimum will become the true minimum. And what will happen is that the universe will make a first order phase transition, and at the end of which the vacuum expectation value of this complex scalar field is non-zero anymore. And the fluctuation around this valve can be parameterized in terms of one scalar that will be massive, and it's a massive boson. And then if you don't have explicit symmetry breaking terms, also by the angular fluctuations are described by a pseudoscalar that is called usually the majoron. Moreover, the right-hand neutrino will acquire mass that is simply given, like in the Higgs model, essentially simply by the product of the couplings in this term with this complex scalar field times the vacuum expectation value. So it's very simple. And this is a very old model that was introduced even in 1981. While there is a new interest now, the new interest mainly was triggered by the discovery of gravitational waves. And so, since it was very well known in electron baryogenesis that you could produce gravitational waves in a first order phase transition, that, as we have seen, is also needed to produce a matter-antimatter asymmetry, people started to be interested. But since, on the other hand, we haven't seen any new physics at the electron scale, the attention was kind of shifting toward the other possible first order phase transition in the early universe. And this framework provides you exactly with this kind of freedom of, especially on the scale of the new physics, to essentially use the gravitational waves as a way to explore the presence of new physics in the early universe. But it's not the only one, as we will see. It's not only gravitational waves, but as we will see, this majoron model is interesting also for completely independent reasons. Anyway, I will refer to the dark sector as the right-hand neutrino plus this majoron and this massive boson, and the visible sector as just simply the standard model particles. I don't know, are there questions? Is everything clear?
Just to confirm, this dark matter, I suppose that it will be long-lived because there is no preserved visible symmetry. So
yes, no, and here, yes, this is a very good question because I talk about many things, and there can be a confusion. But at the moment, now in this extension, I will not consider a dark matter anymore. And that's a good question because, actually, we would like to introduce dark matter in this picture. I told you that I have a personal solution on dark matter that I'm not talking, I'm discussing here. And in that case, yes, you have a right-hand neutrino. You have to add additional terms in the Lagrangian. So, but within this picture, there won't be any candidate of dark matter. So that's a very good question. I don't want to make confusion. So here I will not address dark matter, but if you wish, you can still do leptogenesis because you still have the right-hand neutrinos in any case. But a drawback of the picture is that there is no candidate of dark matter. Indeed, this is something we are considering to do it. We try to do it actually, but as we will see, probably this is a question for the end. If you try, for example, to introduce a mass for the majoron, and you want the majoron to be dark matter, this has been considered many times. This is a traditional, this was a traditional kind of cosmological application of this majoron model. Then this is incompatible with having a first order phase transition and therefore gravitational waves. So therefore, either you do one or the other. And so I will do gravitational waves. And so in my talk, the majoron will be strictly massless, and so it cannot be the dark matter. So you are correct. There is no dark matter in this picture. So in another talk, I could talk about how to extend it to give to have a dark matter candidate, but I'm afraid here I will not talk about dark matter. So let's see how gravitational waves are generated in this picture. Essentially, you do exactly the same as you do in electroweak baryogenesis. So what I'm saying is completely mutuated borrowed by electroweak symmetry breaking, gravitational waves in electroweak symmetry breaking. So what you do, you have to introduce thermal effects and to build an effective potential that essentially is sensitive to the particle content of your model. In our case, it will be dominated by the right-hand neutrinos, as you can see, by this also the presence of this complex scalar field. What you can show, and this is actually very general, applies also in electroweak symmetry breaking, is that this effective potential in the end, when you do a kind of high temperature expansion, takes a polynomial form. There will be additional terms, actually logarithmic terms, but essentially they are completely negligible. So you can show that in a very general class of models, this effective potential will have this kind of form. And the terms, however, the coefficients are temperature dependent, and they can describe a first order phase transition. This is a typical dynamics of this effective potential. At very high temperature, as you can see, the web of the field is 0, and so you have symmetry restoration. And then, as I was telling you, there is a temperature. When the temperature drops down, there will be a temperature when you form a second minimum, a non-zero value of your field. And then this minimum actually will become the global minimum below a certain critical temperature. At this point, by tunneling, you can a certain portion of the universe, by bubble nucleation, can make a transition from the false vacuum to the true vacuum. And you can show that if the phase transition is not too strong, this happens around a very precise temperature that I will indicate as a T star. And actually, this transition happens very, very quickly. What here I highlighted is this coefficient mu tilde that will describe the presence of a barrier at 0 temperature between the two minima. In this picture, as you can see, when the temperature goes to 0, there is no barrier anymore. So this mu tilde is 0. But if this mu tilde is non-zero, there will be this potential at 0 temperature will be modified. It will introduce a barrier. And the presence of this barrier is important, as we will see, because it can enhance the strength of the order phase transition and can enhance the production of gravitational waves. By the way, I should say that in the standard model, in order for the validity of this picture, you will need a X mass below the W mass. That, of course, it's not true. We know that it's not true. So that's why there is no, in the standard model, there is no first order phase transition at the electroweak symmetry breaking. And so therefore, you cannot do electroweak baryogenesis, and you cannot generate gravitational waves. I don't know, are there questions at this stage?
What would be the order of magnitude? So what would be the order of magnitude this critical temperature in that model?
That's a very good question. In the electroweak baryogenesis is essentially given by the vacuum expectation value of the Higgs, so therefore the electroweak scale. And but in our case, I didn't tell you anything about this vacuum expectation value, so it will be a free parameter essentially. So that's the beauty, is that now we are free, and we can explore all the energy scales in the early universe essentially. If you have a favored model with a favored scale, then you have a prediction in your model. But here we don't have any prejudice at the moment, let's say. But just to start, let's consider a scale that is much higher than the electroweak scale, because we have in mind the typical CISO models with and these by the way, also since the Majorana masses have a raw order of this vacuum expectation value times some constants, therefore the scale that you expect are of order of the Majorana masses essentially. So in a normal CISO, they can be 10 to the 10 GeV, 10 to the 12 GeV. So we are talking about very high scales.
This will be larger than the Casas-Ibarra bound from leptogenesis, something I tend to
It can be anything you like. It can be anything you like, really. At this stage, you are agnostic. You are really agnostic. So you are hoping to find signals in the gravitational waves that will tell you then what is the scale of new physics. So it's really a bottom-up approach. Okay. From the effective potential, you can calculate the so-called Euclidean actions that gives you the probability of bubble nucleations per unit volume and per unit time. When this Euclidean action, let's say when you are above the critical temperature, this Euclidean action goes to infinite. And so, as I was telling you, the probability of nucleating bubbles is 0. On the other hand, when the temperature tends to this T0 temperature that was in this potential, then essentially the Euclidean action goes to 0, and essentially all the universe will have made a transition to the true vacuum. It has been shown many years ago by Linde that at finite temperatures, this Euclidean action can be replaced by a 3-space action divided by the temperature, essentially. And so a spatial Euclidean action that can be calculated once you have the potential. And you find a certain solution also for the field. And the solution that you can find is essentially what we call a bubble. So this will be for a typical solution in electroasymmetry breaking. This is the typical profile of the field during the phase transition. And you can also, in the thin wall approximation, find an analytical solution. So inside the bubble, the universe still is in the vacuum expectation value has already made the transition to the true value, while outside you have it's 0 essentially. So while the bubble expands, all the universe will gradually make a transition to the true vacuum value that is non-zero. And Majorana, and in our case, our right-hand neutrinos will get Majorana masses. Now, for gravitational wave production, it's usually you introduce certain parameters, this beta over H star and this alpha, that are nothing else. Beta is nothing else than the logarithmic rate of the bubble nucleation rate, the logarithmic derivative essentially, and the inverse of this parameter, it's essentially connected to the duration of the phase transition. Indeed, this is an inverse time dimensionally, and the inverse of beta gives you a time scale that is essentially tells you what is the duration of the phase transition. When you take, and as I said, we will consider cases where the transition is very quick around a certain value T star. What is this T star? Is essentially the percolation temperature, that it's usually defined as the time when a certain fraction of the universe is filled by bubble, typically 70%. But the exact definition, fortunately, doesn't enter in the prediction, in the calculations, because as I said, even if you change slightly the definition, the temperature T star will very slightly change. So in the end, you get more or less the same answer. So there is a very slight dependence. If you calculate the expansion rate at this T star, this gives you the inverse of this. So the comparison of the two rates is an important parameter that can give you information on depending on T star and on the Euclidean action also at T star. So if you have the effective potential, you calculate the Euclidean action, you are able to calculate T star, and you are able then to extract this beta over H star parameter. By the way, the inverse of this parameter is nothing else than the duration of the phase transition divided by the age of the universe, roughly speaking. So it's essentially what is the fraction of time that takes to the phase transition to occur, okay? During the age of the universe at this time. Another parameter is the strength of the phase transition. That is nothing else than the latent heat that is freed in the phase transition compared to the total energy density. So clearly, the bigger is this latent heat, the stronger is the phase transition. In our case, since the phase transition happened in the dark sector, this alpha is actually expected to be less than 1. So the transition is not that strong, and that's good because actually we don't know how to calculate the gravitational wave production when alpha is too large. So we will be in a regime that I will comment on that where more or less we know what is the gravitational wave production, where alpha is less than 1. And by the way, there is another point. In certain situations that I will consider, the temperature of the dark sector could be different from the temperature of the visible sector because the dark sector will decouple. And in that case, you also have to introduce a strength of the phase transition in the dark sector. So these you have to take the ratio of the latent heat calculated at the temperature in the dark sector and dividing by the energy density in radiation only in the dark sector. So in the calculation of the gravitational waves, also this parameter will enter if you have this case. Once you have these three parameters, you can calculate the gravitational wave spectrum. And there is by the way, the gravitational wave spectrum is nothing else essentially the energy density in gravitational waves within a certain interval of frequencies. This is the exact definition, essentially. So it's the distribution of energy density in gravitational waves in frequencies. And then you divide it, as usual, by the critical energy density in a way that you see the contribution to energy density parameter from gravitational waves. If you integrate over frequencies, you indeed obtain exactly the total contribution from gravitational waves to energy density parameters. That obviously has to be much smaller than 1, essentially. What simulations have shown is that there are 3 contributions to this spectrum. One comes from bubble wall collisions. So when they bubble wall collide, they produce gravitational waves. One comes from the turbulence of the plasma between bubbles. But then recently, well, let's say 10 years ago, it was noticed that actually in this regime where alpha is not too large, the dominant contribution comes from the formation of sound waves in the plasma and propagation. So these sound waves also radiate gravitational waves, and they give actually the major contribution to the gravitational wave spectrum. And this is an expression that can be analytically derived in a certain model. It's called sound shell model, and it has been also verified in numerical simulation. And it works very well when alpha is not too much larger than 0.1. You have different, now here you have different factors entering very quickly. There is an efficiency factor that essentially is the fraction of energy density that goes into gravitational waves. You have a spectral function shape that can be also derived analytically. And what is remarkable is that below a certain peak frequency, there is a certain power law, and then above a certain, that is essentially the power spectrum is growing, the spectrum of gravitational waves. And then above this peak frequency, it decreases. So there is a peak a very nice peak in this spectrum that is very indicative also of the scale of new physics that where you produce. Essentially, it's proportional to the to the temperature of the phase transition. That, as we just discussed, since it's not fixed, but it should be extracted experimentally. Therefore, the position of this peak will tell you essentially the scale of new physics. That's very nice. Also, you have to rescale everything to the present time because we observe gravitational waves at the present time. And then there is I will say, trivial redshift factor that you have to take into account to rescale everything to the present time. And it can be calculated it's a calculation of within the Friedman cosmology. It's a standard calculation. Once you do this, you put everything together, you have a numerical expression for the gravitational wave spectrum. There is also the bubble wall velocity that enters, and you can see there is this beta over H star parameter, this alpha, and this is taking into account, this actually, this suppression factor, unfortunately, has been discovered quite recently. By the way, one of the authors was Graham White, that is here now in Southampton. And this takes into account that gravitational waves are produced during phase transition only during a certain stage. So not during all the phase transition. So you have to take into account that the duration of gravitational wave production is a very short time during the phase transition. That is also a short time during the total age of the universe. And this further suppresses the gravitational wave production. This is the typical shape of the spectrum that you get. And these are calculated just putting by hand the value of alpha and beta over H star. So there is no model behind this. So this is not a model, a calculation made starting from an effective, a three-level potential, calculating the effective potential. This is something we did preliminarily just to play a little bit with the parameters. But these spectra gives you a little bit how well this kind of observation could measure the scale of new physics. So the peak of the spectrum will give you the scale of the new physics. And here we choose the scale of new physics in a way that this spectra will enter the sensitivity of future gravitational antenna. Well, this is LIGO is an existing experiment. So we have to wait for new experiments to see something reasonably. This is the famous LISA satellite. This is the Einstein telescope that is planned to be built before LISA. We will see. But anyway, what is interesting is that tuning the knob, so changing the frequency, essentially gravitational waves make possible to test different scales of new physics. So we started from naturalness that was telling you the scale of new physics at the electron scale, and now we are in a kind of a framework where any scale is possible. So whatever is your favorite scale, you can hope the gravitational waves will find the scale of new physics where you expect to be, essentially. Unfortunately, by the way, maybe you are noticing that if you go to very high scales, for example, those favored, we were saying with Antonio before, by the traditional seesaw, you are much above the range of future gravitational antennas. This has been noticed by many people. Now let's see a minimal model. So you say, okay, this is artificial, give me a model. If I start from a usual three-level potential, so a quartic potential with a sombrero hat, essentially, and you calculate the one loop finite temperature effective potential, this mu tilde term is 0. And unfortunately, if you calculate alpha and beta or H star and then the gravitational wave spectrum, you obtain something that is orders of magnitude smaller, about 10 orders of magnitude smaller than the the peak of this gravitational wave spectrum is 10 order of magnitude smaller, completely inaccessible to the experiment. So what you have to do is to add an auxiliary real scalar. And this is a trick that has been actually done initially in electroweak baryogenesis. People have noticed that if there are two scalars, one can be, in addition to the complex scalar field, that could be a real scalar. And this is also undergoing a phase transition. And if this scalar couples to your complex scalar, and assume now that the vacuum expectation value is much higher than the vacuum expectation value of your complex scalar field, when eta completes its phase transition, you will be left with this term, and this term you can show that will generate exactly this term that will create a zero temperature barrier that will enhance your the strength of your phase transition. Indeed, you can relate mu tilde to this coupling zeta. And this greatly enhances the strength of the phase transition and the gravitational wave spectrum. These are now realistic within this model. These are benchmark spectra that we have obtained in a realistic way. Well, we selected points where, of course, the strength is high enough. Otherwise, again, the bulk of points in this scatter plot will produce you spectra that are not detectable. But anyway, there are some favorable points that could be detected at future gravitational antenna. Here you can see for this benchmark point, what are the value of the critical temperature. In red, I highlighted a temperature that is around GV. The reason why is that also you get value of right-handed neutrino masses that will be of the scale of T star. Here is the value of the Majorana mass. And the reason why this is interesting is that there are now experiments, a phaser essentially, that is searching for GeV right-handed neutrinos. So there is an interplay between, really in an optimistic case, where you could observe this GeV right-handed neutrino, the signal at LISA, and the two things would really be a very strong signal of new scale at the GeV, so the scale of new physics at the GeV scale. But obviously this is a very optimistic case, but it tells you the complementarity between collider physics and gravitational waves. Now, what we did recently is, okay, but what is this auxiliary scalar? Because here we introduced this auxiliary scalar by hand. And with Steve King and Moinul Rahat, we thought, okay, actually, instead of having only one majoron, you could think of a multiple majoron model, for example, with two majoron, that actually where you start from an effective potential and the Lagrangian that respect now not only just one U1 symmetry, but a U1 symmetry into two different lepton flavor directions, L1 and L3 in flavor space. And you can break first at high energies this symmetry, and then this symmetry, and this will give masses first to the heaviest right-hand neutrino, and then to the two lightest one. Now, you have two complex scalar field, and again, at the end of the high-scale phase transition, this phi3, if it couples also to the phi1, if this zeta parameter is non-zero, this will create a this mu tilde term that I was telling you before. These are three examples for different, let's say, values of V1. There is no production at the high scale phase transition from bubble nucleation, but we notice that actually you would also create global cosmic strings. And if the scale of the high energy phase transition is large enough, there will be also a signal, a completely different production of gravitational wave from global cosmic strings. So the combined signal, the total signal would be a combination. You can pick up any of these cases and any of these three cases, and you can sum and you will obtain a spectrum. For example, you can have a spectrum that is something like plateau, and then you have a bump here. And this will be actually a very, very strong signature of this model, because you have now a combined production of from global cosmic string plus the sound wave contribution with a little bump. We also did a 3-majoron model. You can extend with 3 majorons. So each right-hand neutrino, suppose there are 3 right-hand neutrino, will have its own majoron. And now you will have 2 bumps, actually. The highest energy scale doesn't give you any bump, but the 2 lowest one, because of the mechanism I described in general, the spectrum will be enhanced, and now you can have 2 bumps, and then you have this production from cosmic strings generated from the high energy scale. Actually, within this 3-majoron model, the presence of the value, such a high value for V3, so the highest vacuum expectation value, is quite natural, because this could be related to the mass of the heaviest right-hand neutrino. And this will be even more, I would say, distinguished. Another thing you can do is to, now, so far, we were a very high energy scale, but you can lower the scale of your phase transition and considering a model like this, where you have what we call the split Majoron model. So far, we consider very high energy CISO scale, but you could have also a very low CISO scale, what I call a mini CISO scale. This could be, for example, consider the mass or the Majorana mass that is gives you mass to the lightest ordinary neutrino, for example, in a CISO mechanism. Or it could be simply the scale of some dark sector. So you have certain freedom. But for definiteness, now let me say that there is 1 very low right-hand neutrino and 2 very heavy right-hand neutrinos. By the way, this kind of spectrum was considered in the new MSM, exactly to have a dark matter mass. But as I said, here, I don't have dark matter, as I was saying to Antonius. I want to do gravitational wave production. And so, again, you are free to consider a Majorana mass below 100 MeV of any value. And now there will be a phase transition, 1 complex scalar at high energy, let's say the typical CISO scale energy, and 1 phi prime complex scalar at low energy. And here there will be a phase transition at low scale. And what you have to worry now is about extra radiation, because if you have a majoron, that this will be the leftover of the phase transition at very high energy scale, its energy density, it's diluted by the annihilations of standard model particles, and in the end, the contribution is very low. So at the moment, we are not able to measure such a small contribution. But if you have a low-scale phase transition, then you have a contribution that is sizable, and then you have to worry about these constraints from BBN, helium primordial helium abundance, primordial deuterium abundance, and also CMB temperature anisotropies at recombination are sensitive to extra radiation. As you can see, the upper bound on extra radiation can be expressed in terms of extra number of neutrino species. And this is the typical way these upper bounds are given, because it's, as you can see now, the upper bounds tells you that there cannot be any more 1 full thermalized effective neutrino species, but at most you can have, let's say, 0.5, half neutrino species. A majoron, if your low phase transition happens at 10 MeV, and a majoron will contribute, since it's massless, it doesn't decay, it will contribute a recombination as 0.6. By the way, let me say that this kind of case, when the first Planck satellite data appeared, and there was a first hint of this Hubble constant tension, it was proposed as a way to solve the tension. Why? Because there is a degeneracy between Hubble constant and this number of effective neutrino species, and it was noticed that if you extend the lambda CDM model, including this extra radiation, with, let's say, 4 neutrino species, or 3.7, 3.8, you can get high value of H0 as measured by supernova. And by the way, I think we were the first to consider a model of extra radiation to solve this tension in Southampton at this time. But actually, Steve Weinberg, a few months later, okay, he didn't quote us, but I didn't notice his paper at that time, came out with exactly the solution that I was telling you, where I specifying the nature of the Goldstone boson that is a majoron, but essentially it just proposed this solution as a source of extra radiation. Today, this doesn't work anymore. We have more precise measurements, and we know that just an injection of extra radiation will solve the Hubble tension, but would distort the acoustic peaks in a way that actually you get something unacceptable. So you don't solve. There is not just the Hubble tension, but there are many tensions, and you have to essentially not just fit one parameter in isolation, but you have to provide a global fit of all the cosmological observable and show that you get something better than the lambda CDM model. What I can tell you is that the majoron model that are at low scale provides actually a very good, is one of the best candidates to improve the lambda CDM fit. Indeed, in this paper, they did, it was after Tokyo Olympics, they made a paper called H-Not Olympics, and the majoron model got a silver medal. So what does it mean? It means that it was one of the models that the delta chi-square with respect to the lambda CDM model was about 10. So that 3 sigma was better than the lambda CDM model. What is the trick? The trick is that the majoron will not just provide an extra radiation, but it will also interact with the active neutrinos. And because of that, it will change the free streaming length of neutrinos. And when you do that, you can compensate the extra radiation effect on the acoustic peaks in a way that essentially you do not spoil do not change the position of the acoustic peaks, but you can increase the value of the Hubble constant. What we have noticed is that you can also, at low temperature, essentially you can show that you will have effective interaction between neutrino and the dark sector through the majoron and this phi prime field that would essentially be strong enough that neutrinos, even though now we are below 1 MeV, neutrinos will be decoupled, but if the phase transition, let's say, happens around 100 keV, before the phase transition, you can show that you can have a rethermalization of the active neutrino with the dark sector, and they will reach a common temperature. Suppose that the dark sector decouple at very high temperatures. So you can say that its temperature is 0 before rethermalization. But now this interaction couple active neutrinos, so the ordinary neutrinos, to this dark sector, and they will reach a common temperature that will be lower than the temperature that you expect in a standard cosmological model for the cosmic neutrino background. So this model will predict that if you measure the cosmic neutrino background, you will find a temperature that is 0.8 times the standard temperature, that will be 1.9 Kelvin essentially. This rethermalization also, of course, you have to calculate the extra number of radiation. And in a minimal model where there is only the majoron and one right-hand neutrino in the dark sector, you would produce a 0.46. But as I said, now this is compensated by also an interaction of neutrino with the dark sector. So actually, you will have you will ameliorate the lambda CDM model again. Not only, but we have noticed recently in this paper that this extra radiation, if it is produced before deuterium synthesis, so at 65 kilo electron volt, would actually solve a potential deuterium problem that has been noticed very recently by these authors. These authors, they find as a prediction for the deuterium abundance something larger than what is experimentally observed in the standard BBN. And so they conclude that if you introduce extra radiation at this level, that is exactly what you expect in this model, you will reconcile this tension. So this is very interesting. And why it is very interesting? Because if you are above 65 kV, then the peak of your gravitational wave spectrum is exactly within the new signal of nanograph that has been discovered. Clearly, you need here to get a signal that is, here I'm showing not just a line, but since we go to a large value of alpha, as I told you before, this formula is not enough, and there are uncertainties, so we show bands that are 1 order of magnitude. But you could hope to disentangle. So I tell you straightforward that this gravitational wave production cannot explain the whole signal, but it should be a subdominant contribution in addition to the astrophysical signal expected from supermassive black hole binaries. And so if the deuterium problem is confirmed, then it will be really a priority to try to disentangle this signal from the astrophysical signal. Hopefully, there are authors that have noticed that actually at larger value of alpha, around 0.5, the peak could get an enhancement that it can be actually even very large. However, these are not conclusive results, so it will be very interesting. So I will be, I'm really anxious to wait for new results from so essentially, as you can see, there are two different predictions for the deuterium abundance, and so therefore for this extra radiation, and they are based on different extrapolation of nuclear rates at the energy that are relevant for Big Bang nucleosynthesis. And there is an experiment called Luna in Gran Sasso Laboratory that is measuring these nuclear rates and should soon give us the values at the energy relevant for BBN and tell us what is the correct value. If this deuterium problem will be confirmed, then I think this is one of the best candidates to solve this deuterium problem. And then searching for this subdominant contribution in nanograph signal will become a priority. Okay, I conclude here. This is just a slide that shows you some simulations that gives the suppression with respect to the analytical formula I showed you when you go to large alpha. We are in a dark sector. The bubble wall velocity will be very close to 1. Unfortunately, the suppression is within 1 order of magnitude. Actually, probably it's not so large. So probably we are very close to this line, fortunately. But we have to wait for more numerical simulation for the groups. They use lattice simulation to make these simulations. And they are very CPU time consuming. This is why the progress is very slow. Okay, so I conclude here because I think I went beyond my time. So the generation Majorana mass might have cosmological consequences in the early universe. At high energy, we might see gravitational waves in a future gravitational antenna. While if there is a phase transition at low energy that is justified by these cosmological tensions, and it could also solve a potential deuterium problem, maybe already now there is some subdominant component in the nanograph signal. It cannot explain the whole signal, but it could give some subdominant contribution. And the problem will be then to disentangle it by the astrophysical signal. So this is my conclusion. So thanks for the attention. And I don't know if you have questions.
Thank you very much for your presentation, Professor Pasquale. Antonio have the limited personal
Yeah, he told me that.
Okay. Question from the audience?
Yes, I have a question. It's about the majoron mass. If you want to for the majoron to be a candidate for dark matter, you need a little mass, not massless. So the question is whether you know any mechanism for giving mass to
No,
the...
we know the mechanism. They have been studied a lot. As soon as after the majoron model, that was one of the major goals to get a dark matter candidate. And there are different problems. What you can do, we have explored that case in this paper with Yeling Zhu and then Nimar Fazia, and we introduced in the three-level potential a cubic term that will represent an explicit symmetry breaking term. So it will break the lepton number, and that will give, then the Goldstone boson will become a pseudo-Goldstone boson, and that will give a mass to the majoron. The problem is that also what we found is that this Majorana mass destroys the first order, destroys the phase transition. It will not be anymore first order. And we didn't find we did a different scans, and we found that if this mass is larger than 1 electron volt, essentially you cannot have any more phase transition. So it can be, it has to be very, very small, and therefore actually you don't want the mass if you want gravitational waves. That's why I was telling you, either you do dark matter or you do gravitational waves.
I see. Okay.
Unfortunately, we have found a solution for both. So I don't, and to be honest, and there's also, I'm not an expert on majoron dark matter, but there are other problems with the majoron dark matter in any case. So, but yeah, I do not know how to do both together simultaneously.
Okay, thank you.
But that's
question?
a very, very good question, yes.
More question? No? No more question? Thank you again for your presentation, Professor. And see you the next seminar. Okay? Good afternoon.
Thank you
Bye
for
bye.
having me. Bye. Thank you very much.